truss and beam. As you know, truss element can rotate freely. Okay. For this beam, half beam and maybe half truss. You can imagine something like that. So for this kind of structure, we have a special formula to calculate K for this kind of structure. Okay, where at the left end we use this formula, special formula in yellow box. Okay, at the right end, the left side, we use the normal beam formula. Okay, we have to use two different formula for the left end and the right end. In this case, we have element 1, K1, and element 2, K2. Two different formula. This formula only a special case for beam element with nodal hinge. Okay, and then other steps just similar to the normal beam. The difference only for the step in calculating the K, the elastic, the stiffness of element, and that's it. Okay, any question? I open for any question. This is special only for beam element with nodal hinge. Okay, we have example here. I'm not going to show you this example. Okay, we're not going to solve this because you can look at it by yourself. We already have solution. Okay, here you are already given solution. You can see the step by step. For element number 1, we use the special formula. Okay, to calculate K. Element number 2, we use the normal formula, and then find the total K1 plus K2, and then apply the constraint by using penalty method. Okay, constraint, and then inverse K, and then you will get the displacement. Okay, similar here. And then you get displacement. You can look at it by yourself how the formula should be used. Okay, the next one, we're going a little bit fast because I don't think there's a big problem with that. So the difference only the difference in K, the formula to calculate K. Like I mentioned before, the steps are similar. The difference only for the formula. Okay, the next one maybe we are thinking maybe usually we have seen a few example where the beam in horizontal position. Okay, beam in horizontal position. Maybe you some of you maybe thinking, maybe have thought, what if beam what if that beam element is not in horizontal? What if that beam element is somehow inclined in some angles? Okay, that beam element inclined with angle theta with the horizontal axis. In this case here, we have the formula. We treated that with this formula and what we call oriented beam element. Okay, the case here, the beam element which is not in horizontal position, we call oriented beam element. Okay, similar degree of freedom. All beam element has 2 degree of freedom, which is the vertical displacement V, and then rotation about z axis theta. Okay. For oriented beam element, similar case. It's just that since it is in inclined position, the vertical displacement is not vertical displacement. We have to somehow convert it to a new axis. Usually what we call local axis, from global axis to local axis. Okay, for global axis we have y and x, x and y. For local axis we have x prime and y prime. Okay, now the displacement, the vertical displacement is vertical in local axis, which is y prime. Vertical in y prime axis. And so we have vi and vj, vi prime and vj prime. And then the rotation is still rotation about z axis. Okay, and then this is the formula. Okay, the formula for oriented beam element. Okay, nothing hard about this, nothing too complicated. Okay, if you in this for this kind of beam, or for finite element actually, for the whole chapters of finite element, if you know the formula to calculate k, you know the formula to calculate k, you can solve the problem. The hardest part actually in finite element is really to get k. The hardest part, if you are not given k, you have to derive k on your own. That is the hardest thing, the hardest part to do in finite element. If you already know k, you are given k, okay, you just find the total k and then form the matrix equation, apply constraint, and you will get the answer. This is k formula for oriented beam element. Okay, since the displacement, okay, the displacement for oriented beam, okay, in local axis, in local axis, the x prime and y prime. So we have, so the final answer need to be presented in global axis. Okay. After calculating, after we get from the formula, from the derivation, after we get the displacement, vertical displacement in local axis, okay, we need to transform this Vi and Vj here into global axis, where Vi and Vj has horizontal and vertical component. Okay, so that's why here, as you can see here, we have Ui and Vi. Ui horizontal component, Vi vertical component in global axis. Okay, from local axis transform to global axis, we get Ui and Vi, and then here is theta I. Theta I similar, it's either in global or in local axis. Because it is a rotation about z axis. It doesn't matter whether it is in local axis or global axis. Okay, since it is in inclined position, because initially for beam we have 2 degree of freedom, which is vertical and rotation motion, and then we transform it to vertical and horizontal component. It seems that the inclined beam, and somehow it seems like it has a 3 degree of freedom. It seems that it has 3 degree of freedom, which is the horizontal, vertical, and rotation about z axis. Okay, in global axis it has 3 degree of freedom, but in local axis it has 2 degree of freedom. Okay. Okay, the next one, plane frame. So we have covered beam element. Okay, we covered beam element. Now we move to the next topic, which is the the frame element. And then later will cover grid and then space frame. Okay, plane frame is 2D frame. Space frame, okay, is 3D frame. Similar to truss, we have 2D truss and 3D truss. Now frame, we have 2D frame and 3D frame. It's just the name for frame element. For 2D frame, we call plane frame because the displacement or the degree of freedom in XY plane. Okay, for space frame, the displacement or the degree of freedom in XYZ space. Okay, plane frame. Okay, so plane frame element. If you look at the plane frame element, is actually more like the inclined beam or the oriented beam, because it has a 3 degree of freedom. Okay, plane frame element has 3 degree of freedom in local axis, but for inclined beam or oriented beam, it has 2 degree of freedom. Okay, it has 2 degree of freedom in local axis, but for plane frame, it has 3 degree of freedom in local axis. I can show you here. Yeah, this is oriented beam. Oriented beam, 2 degree of freedom, which is vertical motion in local axis, or axis y prime axis, vi, and then rotation. Okay, 2 degree of freedom. One v and then one theta. For plane frame element, it has v and u and then theta. So it has 3 degree of freedom in local axis. And then, okay, this is the formula for plane frame element. Okay, the formula only formula shown to you here only half of the formula because it is symmetry. This is the line of symmetry. Okay, here we have same value as here, minus 6i over ls here. Maybe because it's the formula is too long. Okay, the formula only written half. This part here symmetry to this part. The bottom left part symmetry to the top right part. It is not zero here. It's not zero. I hope you're not confused. It's not zero here. We have value here, but it is symmetry. same value as here. Okay, it's quite long formula. If you have Excel, we can calculate it faster than manually. Okay, outside the bracket, we have K equals to E over L. E over L is the Young modulus divided by the length, and then multiply by, we have A, the cross section, C is the cos theta square plus 12, I is the moment of inertia divided by L, length square, multiplied by S is the sin theta square. And that means we need information about the E, yang modulus, length, cross section, cos theta, okay, the I, mass moment, and then sin theta. Okay, all that information can easily be calculated. Okay, E, A will be given in the question. As well as I. Okay, what we need to calculate is C. Okay, S and maybe L. Sometimes L will be given, but if not, the coordinate will be given to you, and then yeah, you can calculate L from the coordinate using the formula. Okay, any question about this plane frame element? Okay, no example for this because I think this chapter is quite easy. It's actually, it has the same SOP, same procedure. The difference, like I mentioned before, the difference only the formula to calculate K. Okay, if you know K, you can calculate K, you can solve the problem. Okay, here I only introduce you to the degree of freedom and to formula K. The next one, grid element. We're going a little bit fast. Okay, grid element. It has a. Okay, I try to look at it first. Okay, we have 1, 2, 3. Grid element, we have 3 degree of freedom. Okay, what is it? The first one, vertical motion, V, with the vertical motion, similar to beam. We have vertical displacement V, and then we have rotation about Z axis, theta Z here, theta Zi, rotation about Z axis at node I, and then another one we have rotation theta about X axis, rotation about X axis, which the twisting, okay, the twisting effect. That means grid element, we can use grid element to model a structure where the load applied on the structure that will result in the twisting in that structure. Okay, theta X, which is rotation about X axis. Usually the load is in terms of torque. Okay, when we have torque applied on the structure and it will twist that structure, it will make it rotate about X axis, we can use grid element to model that structure. Okay, and then plus vertical motion and then rotation about Z. Okay, actually the top figure similar to the bottom figure. It's just the symbol used here with different representation. Okay, arrow line with double arrow represent the rotation motion. Theta Zi here, and then theta Xi, theta Zj, theta Xj here. Actually, it's the same thing. The top and bottom figure is the same thing. like I mentioned to you, only the representation, okay, of the rotation. Here we use curve arrow. Here we use a double arrow, a double head arrow. Actually, it is they both the same. Okay, this is the stiffness matrix for grid element. Okay, uh, you need to calculate R. For grid element, we need to calculate R, Rg here, R, C, S, and L. And then from there, okay, so we can substitute R transpose, R we already calculated. Okay, this R, you need to transpose this, Rg, you need to transpose Rg, you get Rgt transpose. And then multiply with the terms inside this bracket, and then multiply by Rg. That's key for grid element. Okay. J here, given this formula, the torsional constant J for a few types or shapes of structure. We have J for channel, J for angle, L shape, C shape here. Okay, Z, and then flange beam, solid circular, closed hollow rectangular, and then maybe you find another shape from the textbooks. Okay, sometimes in in your test, J will be given to you, but sometimes J will not be given, but you should know how to calculate it, because okay, you can get the formula from your notes. In practice, when you work as an engineer, okay, you should be able to calculate J by yourself on your own. J will not be given to you. Okay, I don't think I have to mention this. You should know how to calculate J on your own. If you're given this formula, you should be able to solve the problem. You should be able to know. So that's it. That means that you have to calculate J. What is formula for J? Okay, and then you should be able to relate J with the shape of the structure. Okay, ada soalan? Any question?
Doctor,
Yes.
yang RG tadi,
Okay, go back to RG. Okay.
no, yang apa ni, yang masukkan tadi tu, RG yang capital T tu maksudnya apa ya?
Transpose.
Oh, transpose.
Transpose matrix.
Okay, baik.
Tahu kan transpose kan?
Tahu.
Kan? We switch the column and the row. So
Yeah.
this part here RG transpose, but here another RG here, RG without transpose, the original RG.
Okay, baik. Masih Doktor.
Okay, any more question? Ada lagi soalan? Okay, and then finally, space frame element, 3D frame. Space frame is 3D frame. Okay, it has all the degree of freedom, 3 translation, and then 3 rotation. Okay, translation about x axis, y axis, and z axis. UI, VI, and WI, and also rotation about rotation about x-axis, rotation about y-axis, and then rotation about z-axis. So all 6 degree of freedom. So this is the formula, a very big formula, very big K. 1, 2, 3, 4, 5, 6, 12 by 12. Okay, because this is 12 by 12 because we have 6 degree of freedom multiplied by 2 nodes, node I and node J. So this is the formula for single, okay, for single space frame element. Only for single space frame element, 12 by 12. You need to calculate RS. Okay, this is RS, and then inside that we have lambda 3 by 3 there. What is lambda here? CSZ. And then okay, CSZ D as well. What is D? This is a formula for D, for L. And then from there you need to substitute okay, RS here, transpose, and then RS here, and then okay, all the symbol all these parameters, all the parameters that you need to insert, calculate for this space frame element. Okay. Example here, you can see example 5.5 here is for plane frame. Okay, 2D frame. And then that's it. That's example. Maybe another example you can find in textbooks. And that's it for this chapter. Beam, uh, plane frame, space frame, and grid. Okay, so I open for any question. In this chapter, the most important chapters, most important subchapters is the beam chapter. Because usually when we do test, when we want to try to test you, we test you for beam element. It's either the normal beam, the hinge, or the oriented beam. Okay, as far as I know, up to from my experience, there up to today, there's no question on space frame or grid element. Okay, maybe the question, the theoretical question, what I mean theoretical is just the understanding, the fundamental of grid or space frame. Okay, uh, we can test you on that, but the calculation for space frame or for grid element, since the key, the size of what we call the size of formula and the size of for matrix is too big, and then even it will take too long to complete it. So that's why we never test you on space frame or grid. Okay, usually we only ask a theoretical question, the fundamental of it, and just how how uh, how many degree of freedoms. Okay, sketch the element with the degree of freedom and something like that. But never ask you to, or we never ask the student to solve the problem, to calculate and get the values. Previously in old format, where we have assignment, individual assignment. Okay, we have given to the student task or assignment on space frame element. That's okay because you have lots of time to do it. Okay, I think plenty of time. Student manage to solve the problem, but in test, I think since you only given about 1 hour, I think that the time is not enough. So we decided on we stick with beam element. Okay, so either beam, normal beam with hinge, or inclined beam. Okay, any question? Okay, ada soalan tak ada? Okay, if there's no question, I think we can move to new chapters. Okay, when is test 2? Anybody can tell me when is test 2?
8 bulan 12.
8 hari bulan 12? Okay, maybe about 1 week 1 week from today, okay? Okay. Test 2 will cover beam element, usually beam element and fluids chapters, fluid mechanics. So I have to cover fluid mechanics today, and then hopefully next week we can finish this chapter. Okay, we have covered structure chapter. Later on you will find 2D structure. We have covered it's not 2D saja, I mean the surface structure, or what we call plate structure. Now we move to fluid problem, fluid mechanics. Within this chapter, we have 2 sub-chapters or 2 problems. The first one, pipe network problem. The second one, flow in pipe. Or to be precise, actually here is fluid flow in parallel plates. Okay, fluid flow in parallel plate or fluid flow in parallel pipe. Okay, first we look at pipe network problem. Okay, as you can see from the picture there, maybe we are interested to know the flow rate inside the pipe. Okay, as an engineer, as a design engineer, maybe we need to design the pipe network, and then we have certain parameters that we need to know, or certain parameters that need to follow, need to be followed, or certain specification. The velocity inside the pipe, or the pressure, or the flow rate. Okay, and then maybe before we design it, before we fabricate the model, before we build the pipe network, maybe we want to analyze. Okay, if we have the certain the pipe with certain length, okay, with the certain length, certain dimension, the diameter of the pipe, okay, with certain pressure, what would be the flow rate? What will be the velocity of the fluid inside that pipe? Okay, by using this analysis that you're going to learn today, okay, you can calculate that. You can know that. Okay, first, let us consider this simple pipe network problem. We have a few sections here. The first part, the first section, let's say we have flow from I to J, node I to node J, with certain flow rate. Q here is the flow rate. Okay, and then when it reach to point J, it split into two section where the two section here can have different length, different diameter, pipe diameter, and then it meet again here, and at the end of that two pipe, the split, and then it again meet here, and then continue to flow inside the pipe. Okay. I think you have are you familiar with the formula, maybe in fluid mechanics? The formula to calculate the flow rate, Q equals to pi d to the power of 4 divided by 128 mu, where d here is the diameter, the internal diameter of pipes, and mu here is the dynamic viscosity. It's the dynamic viscosity, remember, it's not kinematic, the dynamic viscosity. And then multiply by Pi minus Pj. What is Pi and what is Pj? Pi here is the pressure at node I, and Pj pressure at node J. And then divide by L. Okay, this term here, Pi minus Pj divided by L here. Okay, sometimes we call it pressure drop. Okay, we call it pressure drop. Pi minus Pj divided by L is the pressure drop, okay, along this section here, along this length L from I to J. Or we can simplify this equation here. We can write C, we can write it as C multiplied by Pi minus Pj. Pi minus Pj is the pressure difference. Okay, what is C here? Well, we take out L. We take out L from this bracket, put it outside here. So this term here, C, okay, is a constant for this pipe here. It's a constant for this section from I to J. It's constant because pi is constant. D, internal diameter of that pipe, constant as well. Divide by 1 to L length multiplied by mu, the dynamic viscosity. So constant C for that section of pipe, right? And then multiply by pressure difference. Okay. This C here is only constant for that section only, because from this section, from J to maybe different terms here, maybe this is node 1, node 2, node 3. C from here to here will have different C, different value, because we'll have different D, maybe different L. Okay. Next, we want to create the matrix equation. We want to formulate the matrix equation. Actually, this step similar to axial element. If you remember, for structure axial element, okay, maybe in our first or second lecture, we learn about axial element, where we have K equals to AE over L, AE divided by L multiplied by 1 minus 1 minus 1, 1. Actually, it is the same here. Now, we use this formula, is like similar to Hooke's law. If F equals to K multiplied by U1 minus U2. Similar here, Q equals to C multiplied by Pi minus Pj. From there, we can write in matrix equation to get C here is actually, for structure, usually we call this K. F, Q equals to F Okay, Q equals to F. Usually we call this F in structure. R is K, and P here is U. Okay. For this part here, say this part here C, this C here. If you notice, we have C minus C minus CC. If you take C out of this, we take C out of this bracket here. Inside the bracket, we left with 1, minus 1, minus 1 and 1. Okay, in this case, we want to calculate P. P is what we want to find here. So similar as if we relate this to structure problem, U, the displacement is what we want to find. In this case, P, the pressure is what we want to find here. Okay, the formula for usually what we call K, in this case we call R. Okay, for K we call it stiffness matrix or the elasticity here, this matrix, or in this case we call flow resistance matrix. The symbol is R. And then if you want to simplify this, actually we can take this out. We can take this pi d to the power of 4 divided by 128 L mu outside this bracket, and then we left with 1 minus 1 minus 1 1. Okay, so that's more, I think, simpler formula. Okay, take it outside and then left with 1 minus 1 minus 1 1 inside the bracket. Okay, so this we're going to solve this. Okay, so that we can see, so you can see clearly how we implement the equation, how we implement the formula. Okay, we will try to solve this problem. Okay, let's say we have this simple pipe network problem. Okay, the fluid flow from left to the right. Okay, where the pipe section has different length and then different internal diameter. For example, the first section here, section number 1, length 70 meter, the diameter equals to 10 cm. Okay, second section, length 50 meter, diameter 7.5 cm. Okay, length number 3, section number 3, similar to number 2. Section number 4, length 50, diameter 5 cm. Okay, section number 5, similar to number 4. And then the last section, section number 6, the length and the diameter similar to section number 1. Okay, so all the parameters, the length, the diameter given, already given. So we should be able to solve the problem. And then what else given here? Pressure at node 1 given already. Okay, 40,000 Pascal. And then pressure at node 6, minus 4,000 Pascal. P6 minus 4,000 Pascal. Okay, pressure at node 1 and node 6 are given. What we need to find is what are the pressures at pressure node 2, 3, 4, 5. Viscosity mu given 0.3. So the question asks us to find the pressure at every node. Okay, actually the pressure at every node here is the pressure at node 2, node 3, node 4, node 5. Pressure at P1 and at 6 we already know. That's the constraint, that will be our constraint. And then find the flow distribution in each element. So we will find Q in every element by using the formula for Q. This formula here, Q equals to C multiplied by Pi minus Pj. Okay, part B here, if you try to relate to structure problem, is actually similar to finding the elongation or the stress, strain, and then the elemental force. That means it is easier if we create another table to calculate Q here. Okay, even though the answer already given to you, but I've shown you how to do this. Okay, cell. Okay, it's better for us if we copy this. Put the title first. Okay, class example. Class example. This is a pipe network problem. Okay, FE table standard element. Okay, this time we want to calculate R. We want to calculate R or C. C, and then from C we want to calculate R and the flow resistance matrix. Element, and then we need to know what is node I, node J. Okay, from here the formula to calculate R. Here we need what we need is pi d to the power of 4 divided by 128 L mu. Okay, we copy that. Okay, the formula. So that means to calculate C, the terms inside this is C. C. To calculate that, we need pi. We don't have to write pi. We put D there. D, L, and mu. Okay, type my mu symbol. Okay, insert, and then we can find C. C is pi times D to the power of 4 divided by 128 L mu. That's C. Okay, from there we can find R. In this case, okay, it is already given. Element 1, 2, 3, 4, 5, 6 already given. So we just follow that. 1, 2, 3, 4, 5, 6. For element number 1, node I is 1, node J is 2. Element 2, 2, 3. Element 3, 2, 4. Element 4, 3, 5. Element 5, 4, 5. And then finally 6. 5, 6. Okay. Element 1, D is 10 cm. So we need to convert to meter. Okay, we need to make sure the units are all uniform, since we are going to deal with P1, P6 in Pascal and mu in Newton second per meter square. So that means all the length should be in meter. Okay, so D 10 cm, D1, D for element 1, 10 cm, 10 E minus 2. Okay, E minus 2 means centi. Length 70 meter. For element number 2, D is 7.5 centimeter, E minus 2, length 50 meter. Okay. Element number 3, similar to number 2, 7.5 E minus 2, length 50 meter. Okay. Element number 4 and 5, D 5 centimeter, length 50 meter as well. 5 E minus 2, 50 meter. And then lastly, element 6, D 10 cm, 10 E minus 2, and then length 70 meter. Okay, mu is the same for all, 0.3. And then we can calculate C, which is, we put formula C equals to, type formula equals to bracket, put bracket first. We use pi here equals to 3.142. Pi equals to 3.142. That's pi multiplied by D to the power of 4. Close the bracket. Divide, open new bracket, 128 multiplied by L multiply mu. Mu which is G6. Close the bracket. And then enter. Okay, C, drag down. Drag down to calculate all C, all other C. Make sure the unit, not unit, sorry, the decimal places, 2 decimal places, 1.17, 5.18, that's enough. Okay, from there you can calculate R. Put this R1. Now we can calculate R. We need to put label here. Okay, for this problem, we need to find P, the pressure. Okay, since we want to find P, we're going to use P as the symbol. Okay, for this time, P only 1 degree of freedom because the pressure only in one direction. We have only one direction for pressure. We don't have pressure in X, pressure Y, or pressure Z, only one pressure. So 1 multiplied by number of node, which is 6. So 1 multiplied by 6, the size of the matrix is going to be 6 by 6. So we're going to have P1, P2, up to P6. Similar here, 1, 2, 3, 4, 5, 6 equals to transpose okay. Okay, prepare this for all 6. R2, R3, R4, R5, R6, and then finally total R. R1, R2, R3, 4, 5, 6. Okay, save first, save as. Example. Okay, so we want to calculate R. Okay, first R1, node 1, node 2. So we put there, just put yellow there to show that this is space to be occupied by the numbers. R2, 2 and 3, which is there. R3, 2 and 4. Okay, R3, there and there. Another one here and here. R4, 3 and 5. R4, 3 and 5. Okay, and then R5, 4, 5. R6, 5, 6. Okay, that's the location. Okay, for R1, remember C, we have C here, multiply by 1, multiply by -1, -1, and 1. We have C there, goes to C, here multiply by -1, minus that. Okay, there minus and positive there. For R2, do the same thing. Now you see for element number 2, here multiply by minus, okay, that here is equals to that, here equals to that. R3, Okay, here minus okay, I think you get the idea how to do this. Okay, minus that. Five. And then 6. Okay, so we get all R1 to R6. Okay, I think you have the idea how to get from here, from C to R here. Use this formula. And then total. This is the easy part. Equals to R1 plus R2 plus R3 plus R4 plus R5 plus R6. Control Shift Enter. Okay, we get total R. Okay, any question? Ada soalan? Okay, tak ada soalan. Okay, next we proceed to the equation. Okay, the matrix equation. Okay, the formula is equal to, the formula equals to Rp equals to Q. Rp equals to Q. Okay, I put the formula here. Rp equals to Q. Okay, if you want to relate this to structure problem, Ku equals to F. Similar thing. Ku equals to F. Now we have Rp equals to Q. We have R here. Okay, time P equals to Q. Okay, so in this case, okay, there's no mention about Q here. There's no mention that the flow rate inside here at node 3, flow rate at node 2 equals to something. So it's not mentioned. It's like there is no F, no load applied to it. So we just put 0 there. 0. Okay, the problem is just, it's like for structure problem, we apply no external force on it. In this case we apply no external flow rate on it, so 0 value. And then we can apply constraint. Okay, constraint by try penalty method. Okay, copy. So penalty method, we need big number C. Okay, very big number equals to 1e minus 30. Sorry, 1e 30. It's not minus, sorry. 1e 30. Very big number. And then constraint. Our constraint is P1 equals to 40,000. Okay, from the question here, P1 40,000 Pascal. P6, okay, P6 minus 4,000. P6 minus 4,000. Okay, so we want to apply constraint P1 and P6. Okay, change color, change to green. Okay, P1 here plus C here equals to original value here is 0, right? Sorry, put here plus original value plus, okay, M76 mean this cell here original value is 0 plus C multiplied by the constraint P1. Here at P6, original value there plus C, and here original value-nya 0 there plus C multiplied by P6 there minus 4,000. Okay, then inverse. Okay, R M inverse and then we can find the pressure, or we call it nodal pressure. Okay, pressure at node, which is this value here, the value we want to find. Okay, matrix multiplication, M mark, R inverse multiply by the Q there, close the bracket, Control Shift Enter. Okay, just the number, maybe 1 decimal point. Okay, unit Pascal. Okay, that's the answer. And that's the pressure at node 2, node 3, node 4, and node 5. Okay, any question? Okay, ada soalan? Kalau ada soalan boleh tanya.
Doktor,
Ya. Ya.
boleh explain tak dekat yang matrix constraint.
Okay. Constraint penalty method, okay.
C equal to yang satu tu, itu memang nombor dia ke ataupun dapat daripada mana?
Ni, saya letak YE30 ni, saya letak.
Oh,
Kan ingat saya explain banyak kali dah ni, we choose the very big number. We choose a very big number. So I prefer to use 1E30. 1 darab 10 kuasa 30.
okey, faham.
Okay.
Doktor, lepas tu boleh tak explain yang komen dekat yang equal yang dapat warna hijau tu?
Here.
Ha.
Okay. The green point here, green cell here, I highlight it green because I want to show that this is the area or location that we apply the constraint. Okay. For this part here, original value is 1.17, right? 1.17. The formula is to apply the constraint by using penalty method. The point here, or the location here, you need to add with C. So when 1.17 e to the power of minus 7 plus C, very big number, so we get this. As if the as if the initial value here, okay, dia kena telan. Tenggelam, kita tak nampak dia. Yang kita nampak ni, that very big value. That's why we need to use very big value, so it will make the initial value insignificant. Dia akan menjadikan initial value itu jadi tak significant. Kita tambah dia dengan C, dia akan membuatkan C tu yang jadi sangat besar kat situ, tambah dia C yang kita nampak. Initial value tenggelam. That's the reason we need to add with very big number there. 1e to the power of 30. Okay, sometimes ada orang suka use 1e to the power of 20. It's okay, it doesn't matter. But I prefer to use to the power of 30. That's the reason. Okay, and then this part here, initial value there, which is 0, plus C multiplied by the constraint, which is P1. Okay, P1 is the constraint. We want to fix that 0.1 equals to 40,000 Pascal. So that's why we put here, C, initial value, plus C multiplied by constraint. That's formula. Dalam note, if you refer to the note, that's how we apply the constraint. By using penalty method. We have another method which is direct elimination method. But this one is penalty method. Because usually I show you direct elimination method, but this time I want to show you how we use penalty method so that you're familiar with both method. Similar to this part here, because we want to apply constraint at node 6. So we apply the same thing. Okay, add C we get C value here because initial value 1.17, similar to the value here, very small, plus C, which is very big number. So we get C there, we can only see there. And then here, initial value, which is 0, plus C multiplied by P6, which is minus 4,000. That's how we apply the constraint by using penalty method. Clear tak itu saya explain? Faham tak?
Okay, clear Doktor. Thank you.
Okay, come. Any more question? Any more question? Okay. So I would like to share with you. I would like you to know that from my previous experience, this chapter is this part is the chapter that student most love. I think most like, paling suka. Okay, usually student will get full marks for this part. Okay, if in test 2, right, we have beam question and flip question. Okay, usually for flip question, this part student will get 25 out of 25. Okay, or if not, about maybe 24 out of 25. That's the normal marks. If you get less than that, that's not normal. So you are below average, because every student will get either 25 or 24 for this part. Okay, if compared to other chapter, this is the easiest. I think based on my experience, based on student performance, this is the easiest chapter that majority of the student can do this, can get full marks for this. Because the formula very simple, straight to the point. The matrix is not too big, very small matrix. Okay, and then we continue part B. That's only part A, find the pressure at every node. Part B, find the flow distribution in each element. Find flow distribution. Okay, flow distribution, we go back to the nodes. Okay, we need to use the formula, this formula. So I copy the formula first. Snip. Okay, let me bring this down. Okay, we need to find Q. Part B asks us to find Q, the flow distribution inside the pipe. So we need to calculate Q. To calculate Q, we're going to use this formula C. C, we already know from here. Okay, from this part here, this is C. And then what else we need? We need PI and PJ. PI and PJ here is this part here. And then we can calculate P there. So what we need here, we need another table, element, node I, node J. Okay, and then I think C, we need C, we need PI, PJ. And then you can calculate PI minus PJ first. PI minus PJ, and then Q which is equals to Pi minus Pj C multiply Pi minus Pj. Okay, element 1, 2, 3, 4, 5, 6. Okay, I think this part here similar to this part. And C here similar to this C here. Okay, Pi. Okay, for element 1, I is equals to 1, J equals to 2. That means this is P1 and this is P2. P1 40,000. P2 35024. For element 2, 2 and 3 equals to P2 and here is P3. For element 3, 2 and 4 equals to P2 and P4. Element 4, 3 and 5, P3 and P5. Here for 5, P4, P5. And then finally element 6, 5, 6, P5, P6. So Pi minus Pj equals to Pi minus Pj here and then Q equals to C multiplied by Pi minus Pj. Okay, small number. Okay, I think we can change this to scientific. Okay, so that's the answer. So you need, okay, here you need flow rate, meter cube per second. On okay, meter cube per second. So this is Pascal, Pascal, Pascal. Okay, so that's it. So we get the answer. Is let's say maybe the question, okay, ask us to find what is the mass flow rate. This is the flow rate, the flow distribution. That means the flow rate, the flow distribution, flow rate. What if the question asks us to find what is the mass flow rate or the mass flow distribution inside the pipe? Can you calculate that? Mass flow rate. So what is the unit for mass flow rate, which is mass kg per second. So we cannot calculate now because there is one thing, one parameter missing in this question. To calculate mass flow rate, we need the density of the fluid. Okay, the density of the fluid. If the density given, we can calculate mass flow rate. Okay, that's easy part. If you want to calculate mass flow rate, kg per second here, you just need to multiply Q with the density. Q multiply rho. Okay, m dot mass flow rate equals to Q multiplied by rho. So you get mass flow rate. So that's it. Ada soalan? Any question? Okay, kalau tak ada, saya ingat kita we stop here. I will share this example, okay, in WhatsApp later. So next, so now we going to record the attendance.